Good day, Professor Aliyev. In this video, I'm going to present my hard problem assignment. First chapter was assigned to me. Shortly, this chapter is about fascinating formula discovered in 17th century by Christian Huygens and Blaise Pascal. Gambler's ruin formula. This chapter illustrates its applications by giving examples such as lawsuit of Czarine commissioner, elections of chairman, and estimating the average travel of a photon from the center of the Sun to its surface. The name first misled me to the impression that I will learn how to count cards or maybe guessing in casino using this formula, but the gambler's ruin formula is a bit different. However, the case is as following. It relates to cases where two players, A and B, play a game of chance. They stake 1 unit of money on each gamble until one of the players goes broke. The gambler's ruin formula gives the ruin probability for each of the two players. Then this chapter goes on by analyzing the facts in the famous lawsuit of Czarine commissioner. Shortly, Czarine got unlimited credit line from casino, and he was cut off only when his gambling debt passed the 3 million mark. He was then discharged of debt by the state law, and after the court, Czarine received a federal tax assessment claim from the Internal Revenue Service demanding tax payment on the sum that was discharged from him, which has defined as an income. However, he was then dismissed from the taxes on the portion of the debt by the casino, the debt that discharged by the casino. The reason of which mentioned in the chapter is that Czarine stated that there was no cash money in exchange between Czarine and casino. The only thing that was exchanged is chips for gambling. And only because court didn't properly evaluate the monetary value of the chips, this happened. The gambler's ruin formula enables us to quantify the monetary value of the loan. Czarine was playing the game of craps, a dice game played with 2 dice. You can make bets in different ways, but he preferred so-called pass-line bets. And the probabilities are given as following. The probability of a player winning in this pass-line bet is as following, approximately 0.493, and similarly the probability of player losing or the casino's winning, the same thing, is 1 minus the previous probability, is approximately 0.507. So when the events turns out in favor of player, he doubles the amount of bets, otherwise obviously gets nothing. Then the chapter proceeds by explaining the role of the formula in this case. Here's the classical gambler's ruin formula. Probability AB equals 1 minus q divided by p to the power a divided by 1 minus q to the power q divided by p to the power a plus b. Here a is the amount of units of money which player starts with. B is how much he wants to increase his money from A. P is the probability of increasing 1 unit. Q is decreasing, of course, and it equal to 1 minus P. A plus B is the target stake, or how much money is in mind of player to win. AB is the probability which is found by the gambler's ruin formula, that the gambler reaches the target stake of A plus B without first having gone broke. Also, there is an interesting property of this formula that when Q equals Q, or in other words, the game is fair, which means that probabilities are 1 divided by 2. This formula can be rewritten as A divided by A plus B. It is stated that the most reasonable move would be to bet as much as possible, which Czarine did, and it has been calculated that a credit line of $3 million, this value is 195 $100,000 in total. So to achieve max probability of winning target, then the best thing the player can do is to bet outright, or the house limit defined by the casino. Zarin did the same. He bet max value of $15,000 each time. And here we assume 1 unit of money as a $15,000 and $3 million in debt is 200 units of money. And one thing also mentioned in the chapter is that the conditions of the game are like this. The player will owe nothing to the casino if he goes broke, and the player will go home with a profit of B units of money if he increases his bankroll to A plus B units of money. There is also another interesting formula, let's call it auxiliary formula, that the expected value of gain, UAB, is written like this. The variables are the same as previous one. Now, for finding the monetary value, let's say monetary value, we need to first approximate B, and as we said that the most reasonable move would be to bet the maximum amount. So we denote the maximized value of B, we maximize the B and denote it as B star, and it is found that it's approximately equal to 1 divided by ln Q divided by P. And if we put it back to the UAB star, we get e to the minus 1 ln Q divided by P. And again, we put this back to formula to find PAB, we get such formula. So after rewriting formula, we can factor out Q divided by P. Keep in mind that we can only do that because Q divided by P is more than 1. And 1 divided by, because Q is more, probability of losing is Q, and losing is more probable than winning, and anything greater than 1 to the power negative big number, for the big values of A goes to 0. And when we write it as following and put back to UAB formula, we get such a formula. This is a very good result because it is said that if we find the derivative of this with respect to B and assign it to 0, we can find probability of AB, which is found that it's approximately equal to 0.3679 or e to the minus 1, and we can apply this to the David Zarin's case with the variables of A equals 200, P equals like this, 244 divided by 495, Q as follows. We found that B star equals to 35 and UAB star equals to 13. This means that the value of credit line extended by the casino is about 13 units of money. Each unit of money represents $15,000 as we said earlier, so we can conclude that $3 million credit line extended to Zarin by the casino can be valued at $195,000. Now let's look at the case of elections of chairperson of a committee consisting of n person or n people. Here we can choose from the remaining n-1 person the chairman, of course, and probability of being chosen. This is the condition. Of course, some may say that same person can be chosen twice, but in the chapter say that remaining n-1 people can be chosen, and the probability is 1 divided by n-1. This is easy probability to find. And the method to choose chairman is by fair coin. Heads means pass to the right one and tails means pass to the left. And how to find the new chairperson is simple. It's just the one who didn't receive coin will be the new chairperson. Now, to apply the formula, first we denote a random person as a pivot person. Say that, name it Rose, and the person to the left is left, to the right is right. The following probabilities are given in order to find the results. R is the probability that the coin goes first to the right rather than to the left. S, the probability that the coin will travel around the table from right to left without landing at rows when it has first gone to right. It is also representing the probability that the coin will go around from left to right without landing at rows when it has first gone to left rather than right. And the probability is finding as this: r multiplied by s plus 1 minus r multiplied by s, which gives us s, just s. And it's been said that if we can show s is 1 divided by n minus 1 holds true, then the lottery is fair one. We use classical gambler's ruin formula. As we remember, I said earlier, there is an interesting property then when the probabilities are equal, or in our case that we want to prove the lottery is fair, our classical gambler's ruin formula is as in this form: a divided by a plus b. And if you put the variables in the spots, we get 1 divided by n minus 1, which we wanted to prove, and which means our lottery is fair. This is what we wanted to achieve. And for the last, drunkards walk on a line or in higher dimensions with absorbing barriers or random walk. This is demonstrated and used to estimate the average travel of a photon from the center of the sun to its surface. I would like to talk a bit more about this example. However, this video is already too long and I'm running out of time. So thank you for watching this video. Thank you, Professor Aliyev.